Hello, hello, everyone. Great to be here. As I was just telling Sammy and some of the other guys who came in early, I'm not going to be able to do the immersive experience with the green screen today. My I came to the office yesterday. My green screen had fallen. The duct tape apparently is not working as I wanted it to. So I'm going to have a more permanent fixture by the end of this week. So next week can probably resume with if all goes well and the tension rod fits between the two walls that I have behind me, then we'll have the green screen up and running next week. A few things, a few logistics. I had assigned you randomly to breakout rooms, and I'm hoping you're logging on to Zoom. So the only way I can do this is by email, and I'm assuming that you're using your Utah email to join our Zoom lectures from the Canvas page. So the breakout room assignment is going to be based on that email address, not your name, because you can obviously change your name in the profile when you join. So we're going to try the breakout rooms in a second to see if they're working as expected. And the way I do this is I load an Excel sheet, a spreadsheet with your unit, with your UMail and the breakout room. And then Zoom will automatically assign you to the correct breakout room. So I'm gonna go ahead and try that right now, see if it works. It's the first time I'm trying this out. So I'm gonna just try it out. Okay, looks like it's gonna be okay. I'm gonna open all rooms. Okay, have you been invited to join a room? Oh, there are a bunch of students who are not assigned. A lot of students who are not assigned to rooms. Okay, so I'm gonna close all rooms. So let me ask you this. For those of you who were not able to join a room, are you joining Zoom with your UMail or just you're clicking on the link? How are you signing in to Zoom?
I'm just clicking on the link.
The link from Canvas.
Just clicking on the link.
The link from Canvas.
Yeah.
Okay, so when you see your profile, but some of you are joining with, is anyone clicking? So when you say click the link on Canvas, is it the one on the front page, or there's a menu item at the bottom on your left that says Zoom? If you go, is that how you're joining Zoom?
That's how I went.
Yeah,
From the dashboard.
From the dashboard.
I went through the Zoom link on the bottom of the left side.
I think it has to do with how you are signed into the Zoom application on your computer. Because I don't think it matters like which one you're signed into, if it's your school one or your personal one, as long as you click on the link.
Okay, yes, I think that is the correct explanation. So I would like you to sign in to Zoom using your UMail, please, so that these breakout rooms, or if you're using another email, you gotta have to send me that email. It's just easier though if we just use your UMail, because it's your unit at utah.edu, and that's what I'm using when I create these breakout rooms. So if you don't mind, if you have not signed in with your UMail, please leave the Zoom, sign in with your UMail again, and then click that link on Zoom. Is that clear?
I think I was able to sign in without leaving the meeting.
Okay.
But I'm not sure
Can
if
you
it worked.
tell us how you did that?
Yeah,
I did that too.
If you go into the, I don't know, I'm on a Mac, so in the upper left corner, there's the zoom.us and there's an option to sign in. It's on the same.
Oh, so I have a Zoom application. I cannot see that, but you're probably, if you're in a browser, you probably can change that login. So go ahead and change your login to your unit at utah.edu, please, and join in again. Let's
So,
see if
and I
somebody-
think you have to sign in. I don't think you do your UID. I think you do sign in through SSO, and it'll take you to like
Yeah.
an external link through Canvas.
which is LMS-Utah.
Yeah, exactly.
yeah.
And so you don't like type in your email, you
Unit,
like go
yeah.
and sign in through SSO. I think.
Okay, good to know.
It-
You are all
did it
so
work for me?
technology,
Like, am I-
so tech savvy.
Can you tell us if we're like in?
I
been assigned
cannot.
to-
I'm still waiting. So let me try something. Let's see. Okay, so let me see. You should be in, because I have a bunch of rooms here. Yes, I see you, Dali, in group activity 5. You were not
Okay.
assigned previously, I believe.
Yeah, I don't think I was either. So I think
Okay, so looks like we have a bunch of students coming in. So I'm gonna try the breakout rooms again, okay? I still got a bunch of unassigned. Bailey, are you here with us? Dali, did you get?
Started freaking.
Yeah, it's telling me. So there's a bunch of people here, starting with you, Bailey. Okay, now I have Alexander, kind of alphabetical, who are not. I'm not seeing you or being assigned to the correct room. So it seems that you have not signed in using the SSO.
I'm signed in as my first name dot last name at utah.edu. So
Yeah, that's not gonna. It looks like that's not gonna work, Natalie. Try to sign in with the I think LMS Utah. When you sign in, I think it's called LMS Utah. When you sign in, try to select SSO and then put in LMS -Utah.
I just did that. Can you see like my name is on the what do you call that, PowerPoint? I don't know on the group list or not. Like I tried to log, like, so do you see my name on your group settings or not?
Hold on. So let's see, Sophie. I cannot see. Do you know what group you've been assigned to, Sophie?
I think 17.
17. No, I cannot see you in 17.
Okay.
Did I fix mine? Bailey Doucette.
Okay, let me try. Bailey, do you know which room you have been randomly assigned to?
I think it's 11 or 12. I can check though.
Okay, I cannot see you in neither 11 nor 12. I cannot see your name. So for those who use the SSO successfully, can you explain to us how you ended up? On my end, I have the app. I go on the app and I click login. I cannot show you because I have to sign out. But when I log in, it gives me the option, log in with Gmail, with your like personal account or with SSO. I click SSO and I type in LMS-Utah. And then it takes me to log in with the two-factor authentication, and that just automatically brings me into the Zoom as a unit at utah.edu. Okay, I do not want to waste significant time on this, so let's forget about this for a moment for today. I'll try to sort this out offline and send you instructions on what you need to do next time. For today, we will just use the individual names rather than the groups. Unfortunately, it seems that not all of you have been assigned. I still have a lot of people unassigned. Okay, all right. Technical errors. Okay, I'm gonna share my screen. Okay, you will notice that the other thing I also, so beyond the breakout rooms, which we will sort out hopefully by Thursday, I also sent you a survey to ask for your participation in class if you would like, if you're okay being called upon. Now, you know, typically in a physical classroom, everyone is going to be called upon. Oftentimes, you know, if you do not like being put on the spot, I'll give you a heads up. Like I tell you, you know, hey, you're going to be up next, so make sure you think about this problem. And the point is not to stress you out or to scare you, it's to give you an opportunity in a safe environment to try to do critical thinking on the spot. Because in real life, that's how it's going to be. Okay, that's the reality of it. You're going to have to compete with a lot of people who are going to be standing up and, you know, doing critical thinking on the spot. But I still would like to give the option to students who, you know, don't like to be called on the spot. That's why we create the groups, to still give you the opportunity to do critical thinking. And the groups, usually they have different times, you'll have a different member speak out on behalf of the group. So, you know, that tends to balance things out. Thank you for those who filled the survey. Many of you have changed their mind. They want to be called upon, so I added you to the list. And if you want to be out, just let me know. But again, if I know who you are, and I know you're fighting in this class and you're doing your best, you know, that helps me make a final judgment call when putting in kind of the final grades in the class. Okay. The other thing you will notice I did is modules. I've never worked with modules in Canvas, but I'm gonna try to play around with modules a little bit. We'll try them out with linear solvers. And I noticed that most of you started responding to the modules. The first thing I put in the module is a link to this video. And it tells me that all of you watched it. Is that accurate? It's telling me that pretty much everyone was able to see the video. Did anyone not see the video?
I didn't see the video. I'll go out and I haven't.
Oh.
I didn't see it either.
I don't think so.
I didn't see it.
You didn't see it. That's okay. Did you get a notification that something changed in the module? Okay, so now when you go on,
I didn't get a notification.
Okay, that's okay. That's okay. I didn't put anything that the modules are more like to collect files under a certain topic, rather than putting them to collect files and ideas under a certain heading, rather than putting them in the files directory. I think it will be a cleaner way to communicate with each other. So what I wanted to show you is this video. It's a long video, so I'm gonna have to ask you to watch it by yourselves, but to motivate you to actually study linear solvers. So I'm gonna stop the share because I need to share internal audio. And then I'm gonna do the share again, screen share, optimize video clip, share sound, desktop 2. Okay, so I will have to ask you again to look at the video.
This video provides an overview of.
Okay, so NIST is the National Institute of Standards and Technology. And it is a, hold on, I lost everyone. Can you still see me, hear me?
Yes. Yes.
Okay,
Yeah.
somehow I cannot see anyone anymore. Which is, okay, so now I can see you. Okay. Okay. Okay, so this video, the goal of this video is to motivate you for the study of linear solvers, which is the second topic we are going to talk about. And linear solvers are techniques that are algorithms that solve linear systems of equations. We will study those in detail as we go along. But this video is to motivate you on why we study linear solvers. And it was created by NIST,
This
the
video
National Institute of Standards and Technology. Actually, a colleague of mine works there. He is a graduate of the University of Utah. He leads the fire simulation team. So they developed the software called the Fire Dynamics Simulator that simulates fires in enclosures, etc. This particular video is a study of an incident fire that happened in California that ended up killing a few firefighters, sadly. And they explain why. They use methods and techniques called computational fluid dynamics. And part of the analysis requires the solution of a lot of equations and heat transfer problems. And this is the area I work in personally. And in all of what you're going to see when you watch the video, you have large linear systems of equations to solve. So I'm going to play the video a little bit. I'm just going to skip it. I'll let you watch it. It's a little bit long, so I'll let you watch it on your own.
Analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight into the dynamics of a fire that resulted in 2 line-of-duty deaths. On June 2, 2011, a fire in a multi-level residential structure claimed the life of a lieutenant and firefighter paramedic from Engine 26 of the San Francisco Fire Department. NIST examined the fire dynamics of this incident at the request of NIOSH and the San Francisco Fire Department. At 10:45 in the morning, a call was dispatched for a reported fire due to an electrical short. Engine 26 arrived on scene within 3 minutes of the dispatch and reported light smoke conditions. They made entry through the front door with 1 3/4-inch hose line. At approximately 10:54, about 6 minutes after the arrival of Engine 26, Battalion Chief 9 followed the Engine 26 hose line up the front stairs, into the front door, and then down the stairs to the first floor or street level of the house. Battalion Chief 9 had a face-to-face discussion with the victims. During this discussion, Engine 26 confirms that the fire is below them, and Battalion Chief 9 indicates that the attack will be made from the basement level on the B side. The battalion chief exited the building. Engine 26 remained in position near the top of the stairway leading into the basement. This was the last communication with the Engine 26 crew members inside of the structure. Within 11 minutes of Engine 26's arrival on the scene, the large windows that made up most of the side sea wall of the basement level began to fail due to heat from the fire. As the windows broke, fresh air mixed with hot fuel-rich gases in the basement, which increased the heat release rate of the fire. The increase in heat release rate resulted in the rapid failure of the 6 window panels. It took less than 2 minutes for all of the windows to fail. After the rear basement windows began to self-vent, Engine 24 and Rescue 1A tried to make entry through the pedestrian door in the garage to attack the fire, but they were forced back by extreme heat and heavy black smoke. With the pedestrian door between the garage and the first floor hallway open, heavy black smoke began flowing out of the open garage door at street level on side A. Within a minute of this change, the side B door on the basement level was forced open. Battalion Chief 9 reported heavy fire and smoke. Engine 11 tried to make entry into the basement, but they were forced back by the heat. Battalion Chief 9 requested a second hose line. Incident Command attempted to contact Engine 26 several times via radio, with no reply. By 11:02, both Engine 11 and Engine 32 had made entry through the side B door into the basement and initiated suppression operations. At approximately 11:08, the lieutenant and firefighter paramedic from Engine 26 were found in the first floor hallway between the top of the stairs from the basement level and the door to the garage. Both of the Engine 26 crew members died of their injuries sustained in the fire.
Okay, so I don't mean for this to be morbid, but it's typically events or stories that evoke a strong emotional response in us that tend to stick to us. The point of this is to illustrate how what we're learning in class is helpful in understanding and preventing incidents like this. So this equally applies to like airplanes and airplane crashes where you want to study structural integrity of the plane subject to aerodynamic forces. Now, what the NIST team did using that software is they used the power of computational fluid dynamics simulation to understand what happened. And I'll let you watch the video. And
Between
they
the
ran
basement and-
simulations. They ran the simulations of the multi-story building, and they showed that when they opened one of the doors, it caused a lot of oxygen to come in and move the fire in the direction of the firefighters who lost their lives, which caused them to essentially lose their lives. And that was a big mistake, but it wasn't until they did the simulation where they understood what really happened. Now, all of these color maps that you're seeing, like in this case, they're showing color temperature. I don't know that stupid ad. Okay, it's showing colors corresponding to temperature all the way to 1500 Fahrenheit with red. And the video is going to illustrate how that heat, how that flame has shifted when they opened the door. Now, my point is to solve this problem, and particularly the heat transfer problem, you are going to need to solve a very, very large system of linear equations. And this is what we're going to be learning in this chapter. In fact, we will do a heat transfer problem, but it'll be one-dimensional. It's not going to be as complex as this problem because this takes a lot more training and knowledge to be able to do this. But once you convert this problem into a linear system of equations, the techniques you're learning in this chapter are going to be applicable over there. Okay, so I hope you'll take the time to learn about this video, and NIST is a great place to do an internship if you like this kind of stuff, if you end up liking computing or even other things. They do experiments on fires and fire code, etc. Great place to be at. All right, so and that's the motivation. Now for linear solvers, there's a bunch of learning objectives. There are quite a bit. I'll let you read through those. And last time we had started by discussing what a linear equation is, and the answer we got was that a linear equation is an equation where a quantity is related to another quantity in a linear fashion. In other words, there are no powers or complex functions or square roots or logarithms or signs. It's just simply the quantity shows up, such as the equation 2x plus 3 or ay equals c or 2u equal 5. So some examples as a linear equation. Now, the same applies when you have more than one equation where you're trying to relate two or more quantities together. And we'll do an example from separation for this to be fixated in your mind. And here I'm just going to show two quantities, x and y, that are related to each other. They're part of the same system. For example, one quantity might describe the flow rate of compound A, and y might describe the flow rate of item B, and this is how the quantities are related. This is a system of linear equations. You have two equations, two unknowns. You learned that in school, and you might have three equations and three unknowns, and so on and so forth. Okay. Now, systems of linear equations are essentially ubiquitous in science and engineering, and specifically in my area of research called computational fluid dynamics. Linear systems are used to solve for the pressure, for example. They can be used to solve for the velocity, for the temperature, for all sorts of things. So they are very, very important. And you're going to see linear systems of equations throughout the course when we do interpolation, when we're going to do nonlinear equations, when we're going to do regression. We're going to end up having to solve linear systems of equations. So this chapter is a big deal. All right, so we're going to start with an example from separations. In the following, and you're going to be taking a course on separations pretty soon. What I'm showing here is a separation unit where on the left, you have some solution coming in that contains three compounds, A, B, and C. This solution is coming in at a rate of 10 kilograms per second. That's a mass flow rate. So you dump in, every second you dump in 10 kilograms of this solution. Now this solution, like I said, contains three compounds. A, B, and C. Now the W's that I'm showing on the left, WA, WB, and WC, those correspond to the mass fractions of the compounds. So in other words, when I say WA is 0.2, it means 20% of the mass coming in corresponds to compound A. WB 0.6 means 60% of the mass coming in corresponds to B, and then the remaining 20% corresponds to C. So in other words, to get the flow rate of compound A that is coming in, you simply take the total flow rate and multiply it by the mass fraction of A. So that gives you 0.2 times 10. So you get 2 kilograms per second of compound A, 6 kilograms per second of compound B, and 2 kilograms per second of compound C. Now, this solution comes into this blue unit where our goal is to separate A, B, and C. Okay, so in the first unit, we are gonna try to separate everything into B, and then it goes into another separation unit, and we'll try to separate the remaining, or if we can, separate the remaining into A and C. And so, but this is what happens. What goes into B, we know we can measure what goes into the first unit, we can measure on the upper right. Can you see my cursor? You can see my cursor. Okay, that's great. So on the upper right here, this is what we measure. We measure 0.04 or 4% of compound A, and 93% of compound B, and 3% of compound C. Okay, and then over here at this location, we measure this much for A, B, and C, and then this location, we measure this much for A, B, and C. Now, the question is, excuse me, what are the flow rates at these locations? At this location, the total flow rate of all compounds at this location and at that location. And I'm gonna call those flow rates X1, X2, and X3. I just assign them variable names. You can call them X, Y, Z, okay? We just call them X1, X2, X3. So now you're gonna use your knowledge of this system, what you know about this system. First, that you know the total mass flow rate coming in, you know the compounds of the percentages of the compounds of what's coming in, you know the percentages of the compounds what's coming out. And there's one thing that you need to recognize is that the total mass that's coming in has to leave. So if you add up all the masses, that should be equal to whatever mass is coming in, okay? I'm gonna give you a couple of minutes to try to develop equations. I'm not asking you to find X1, X2, X3 yet. I'm asking you to find the equations that govern how to find X1, X2, and X3, okay? I'll give you a couple minutes. Don't look through the slides. It's not going to help you. It's good to do this exercise right now together, okay? So clearly, you have three unknowns, X1, X2, X3. You need at least 3 equations, okay? And at most 3 equations. So I'll give you a hint. The simplest equation you can think of, what if you add X1, X2, X3? What should they add up to? So think of that. That's one of the equations, right? And you should also know that, you know, the flow rate of A is going to be the flow rate of A everywhere. The flow rate of B is going to be the flow rate of B everywhere. The flow rate of C should be the flow rate of C everywhere. So that should help you develop those equations. Come on, try it out. Just write something down, even if you get one of the equations, okay? All right, I'm gonna call time. Okay, I'm now gonna invoke my wheel of random names. Okay, do you see this wheel over here? So what I did, I got the names of those who are, oh, actually, this is an old name, old set of names. I'm sorry, let me get the, this is from last year, I believe. No, this is from this year, because I see Bailey's name over here. Okay, so now I'm gonna spin this disk and it's gonna pick a name and, you know, share with us your answer, okay? Let's see. Carl, is Carl with us today? Carl. Okay. All right, so let's do another one. Sophia. Sophia.
Yes,
Sophia?
I'm here.
Yes, hi. Yeah,
do
you yeah.
Yeah, I didn't write it down, but I can tell you what it is. Like,
yeah, go ahead.
Okay. Sorry, I'm just waiting for the. Yeah, there it is. Okay. So I just did. You would do the M, the in M, times the WA, and then equal it to M times WA plus like M of X1.
Or X1. So we called M dot at that location. We have to distinguish the variables. So M dot over here is not the same as this M dot, right? So you said WA M dot is equal to X1 WA.
Yeah, and then X2 WA plus X3
X3 W. Correct. Why?
Well, because you know that everything going in has to come out.
Exactly. Exactly.
Yeah.
And then you do the same for B and C. That's right.
Yeah.
Exactly. So thank you, Sophia. So great answer. So what you just exercised is the principle of mass conservation. We're not going to be studying mass conservation here, but I thought it was a fun exercise to do. So just like Sophia described, you simply say the flow rate of A needs to be whatever is coming in as A needs to leave. So WA times 10 is equal, WA at this location times 10 is equal WA at this location times X1 plus WA at this location times X2 plus WA at this location times X3. You do the same for B and C. Or you can say the total mass coming in, 10, is equal X1 plus X2 plus X3, and then pick 2 of the other ones, because you only need 3 equations. You cannot do 4 equations and 3 unknowns. You have to pick 3 of the equations, okay? And so I just happened to pick the total mass flow rate, X1 plus X2 plus X3 equal 10, and then the WA compound, and then the WB compound mass flow rate, okay? Now, the way you would write this, and I'm gonna help you now transition into kind of what you think of linear, how you think of linear systems and matrices. One way to think of this is that you see that in the first, if you look at these equations, you stack them on top of each other, you'll notice that X1, X1, X1 in the first equation, and then you have X2, 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 and then you have X3, 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 and then you have a constant, right? So you'd probably write this as a vector, as a column vector, okay, 1, 0.04, 0.93 times X1, plus another column vector for X2, plus another column vector times X3, okay? And equal 10 to 6, right? That's completely legitimate, okay? Do you see this? All right, I'm just trying to transition the nomenclature now with you. Now, all of this, when you think of it this way, you can convert all of this into a matrix vector multiplication. So what I'm claiming here is that this system of equations that we started with, where you had equation 1, equation 2, equation 3, is actually equivalent to be written as a matrix of these coefficients, 1, 1, 1 for equation 1, 0.04, etc. for equation 2, and 0.93, etc. for equation 3, multiplied by the vector of the unknowns, okay, equal to whatever is on the right-hand side. Does anyone disagree that I can write my system of equations like this? Try it out. Try to do the matrix vector multiplication. What do you get? For the first row of the matrix times the column vector, you get 1 times X1 plus 1 times X2 plus 1 times X3 equal 10. correct? Now you take the second row of the matrix and multiply it by the column vector. You get 0.04 times x1 plus 0.54 times x2 plus 0.26 times x3 equal 2. That gives you the second equation. Same thing for the third equation. My point here is that matrices, moving forward, you have to think of matrices as systems of linear equations, where the first row corresponds to the first equation, the second row is second equation, and so on and so forth. We call this the coefficient matrix. When we start thinking about linear systems, we're going to call this the coefficient matrix. This is going to be the solution vector. It's unknown yet. Our goal is to find x1, x2, and x3. And this is called the right-hand side vector. Okay? We're just defining notation here. All right. So I'm going to move this now. Yes.
So did you just choose a 3x3 matrix because we have the 3 unknowns, so you wanted it to be a square matrix?
Well, what other option could I have?
Because you didn't use WC, did you? Or am I missing something?
You could use W3, but it will be a redundant equation. You would have 4 equations, 3 unknowns, but one of those equations is going to be a repetition of the other equations. So you cannot solve that system like that. Because you have 3 unknowns, you need 3 equations. So you just have to pick 3 of those equations.
Okay, so it does need to be just a square matrix then.
It has to be. That's a condition. Otherwise, you will have an overdetermined system. You will have more solutions than unknowns.
Okay.
Okay. We'll talk about that in a little bit. But yes, so you kind of jump the gun. We're going to talk about the square matrices in a second. But what I'm trying to define here is notation. Okay. So now we moved from a system of equations to something that is simpler looking, AX equal B. Okay, A is a coefficient matrix, X is the solution vector that we're trying to find, and B is the right-hand side vector. Okay, so now how do we solve for X? How do we find X? I'm gonna draw an analogy with a single scalar equation. Let's say like 2x equals 3 or AX equal B. When you're trying to solve a single equation like this, what do? You simply say X is equal B over A. Correct? That's how you would do it, right? If 2x equals 3, then x equals 3 over 2. Is that correct? Yes. Okay. Now I want to do the same analogy with the matrices. Okay, so I'm going to say x is equal b over a, right? But there's a problem here. Can someone see the problem? Can you divide by a matrix?
You can't divide matrices like that.
Yeah, you cannot divide by matrices. It's undefined. There's no definition of matrix division. What do? You like divide per item? It's just wrong. It doesn't work that way. Instead, the notation we use for matrix division is called the matrix inverse. We multiply by the matrix inverse. The inverse of a number is 1 over that number, but the inverse of a matrix is not 1 over the matrix. That's undefined. We just call it the inverse of a matrix. But it achieves the same effect as if you're dividing by that matrix. You've probably seen this. I expect that you've seen it in high school or somewhere before coming to this class, but it's good to kind of revisit this, okay? So then the solution that we're looking after can be expressed as A inverse times the right-hand side. So then the goal of linear solvers is to do one or more of the following. Either find the inverse of A, which is what you probably learned in high school. For small matrices, for 2x2 matrices or 3x3, you can find the inverse easily. For large matrices, it's extremely difficult. Or find an approximation to the inverse of A, or solve the system. Again, we're after X. We want us to solve for X. We're going to find ways to solve the system without computing A inverse. Can you believe that? We don't have to compute A inverse. I'm claiming that we can find X just iteratively, somehow applying a recipe, a formula that allows us to converge to the solution without having to go through A inverse. There are a lot of legitimate reasons for why we want to do that, and we will cover those as we go through this chapter. But for the intents and purposes right now, this is the outline of what the goals of this chapter are. Okay, is to either find an inverse for A, find an approximation to the inverse, or completely find X without finding the inverse. All right. Now, going back to this separations example, I'm giving you here an example of how we would do it in Python. What I want you to do now is hop on your modules and let me show you. So go on Canvas, on modules, okay? And you should see a linear solvers module. So I'm trying to keep Python afloat along the way as we are trying to develop these solutions and these concepts, okay? So if you go on your Canvas, go under modules, you will see a linear solvers module. And in there, you're gonna see 2 Jupyter notebooks that I put in today. Okay, download both of them and put them in your Jupyter Hub or whatever your files are. We're gonna start with linsolve activity1.ipynb. Okay, and I'm gonna share that right here with you. Okay, so you should see something that looks like this. Okay. Coding activity. This is not on TDMA. It's on activity 1. Let's just call it coding activity 1. Okay. Anyone having trouble finding those files, uploading them, etc.? Okay. So now we're going to use a couple of built-in functions in Python to solve this system of equations that we just did together. Okay, so if you see my slides, this is what you will see. Okay, so we're trying to we want to solve this system in Python. Once you have your notebooks loaded, I'll explain to you what the Python code is doing. Okay. Okay, so I'm assuming that you have your Python codes loaded. Okay, so we're gonna.
A small question.
Yes.
Yeah, just a small question. So, how did you get the 2 and 6? Is that the mass flow rate? The 2 and 6, like on the right hand side, is 10 to 6, right?
Yes. So let me go to the previous slide if I can view my navigator over here. Okay. All right, so if you come back here, okay,
yeah.
Now the 10 is the total mass flow rate for this second equation. This second equation is for WA, right?
Yeah.
So the total coming in for A is 0.2 times 10, which is 2, is equal to whatever is leaving of A. So that's what it is.
Okay, yeah, got it. Thank you. Thank you.
Okay. Okay. Okay, so now coming back here, the brute force approach to solve a linear system of equations is simply to compute A inverse, or alternatively use a built-in Python function called solve. Okay, both of these require you to provide, well, the solve function, let's start with the solve function. The solve function requires knowledge of the coefficient matrix A and the right-hand side B. Okay, and this is given in this sample code over here. So I'd like you now to try to implement this over here. So what you want is to define the matrix, to put in the matrix manually, just like I describe it here. Now, I did for those in the Python lectures, so it should be clear to you. The way I'm defining the matrix over here is as a list of lists. There's an outer list, you see the outer bracket, and then I define each row as a list. Okay, so we can do this together. I'm going to open an outer list, and then I'm going to start with the first row, 1, 1, 1. That's list 1, that's row 1. Okay. Now I'm going to put a comma because now we're in the outer list. I'm going to do the second list, which is the second row, 0.04, 0.54, and 0.26. That's the second row. I close that list, put a comma because now we're in the outer list. And then I'm going to go to the last row, 0.93, 0.24, and then 0.0. Okay, so that defines our matrix. The right-hand side is simply a vector. Okay, and we're going to define it as a list again. We're going to do 10 to 6. Now the solution is solve A comma B. Okay, now the solve function, I needed to import it from numpy.linear algebra. It's a package from NumPy. This is the first time you've seen this. Memorize it, okay? Or come back to this notebook so that you know where you're gonna grab the solve function. So I say from numpy.lin algebra import solve, okay? So I'm gonna press Shift Enter to activate this. Then I'm gonna try to run this here. Okay, so I am having issues over here. Oh, I have this type over here. Okay, and this is what it gave me. Now the solve function, if you want to know what the solve function takes, you put your cursor here in the just behind the parentheses, or as you're writing solve, you open the parentheses and you press Shift Tab. You press Shift Tab on your keyboard. It's gonna give you the function signature, or in other words, what arguments does the function take. So when I press Shift Tab, this is telling me solves a linear system of equations or a system of linear scalar equations or linear matrix. So A is the matrix, B is the right-hand side. So that's what I'm doing here, A comma B. And then it's gonna spit out the solution. It's gonna tell me x1 is equal 5.8 kilograms per second, x2 is 2.4, and x3 is 1.7, okay? So that's the first method of solving a system of equations. The second method is to compute the inverse. Now, with the inverse, you do not need the right-hand side, correct? Because the inverse of a matrix has nothing to do with the right-hand side. It's just the matrix itself. Note the difference. With solve, we had to provide A and B. We had to provide the coefficient matrix and the right-hand side. With the inverse method approach, we don't need to do that. Now, to invoke the inverse, you need to bring in the inverse function from numpy.linear algebra. Anyone behind? Anyone falling behind? Okay, great. So from numpy.linear algebra, I also imported inv, which is the inverse function for taking the inverse of a matrix. Now, to compute the inverse of a matrix, you simply type inv of A. So that gives us A inverse. Okay, so let me take these out for a moment. So print A inverse. This is the inverse of the matrix. Now, once we compute the inverse, if you go back to my slides, all you need to do to compute the solution is multiply the inverse by the right-hand side. Now, how do you do this? Unfortunately, you cannot do A inv times B. It might be an undefined function. If I do A inv times B, I'm not sure what it's going to give me. It actually gave me a matrix, which is wrong. Okay, what you need to do is called an inner product, which is at. You use the symbol at. Okay, A inv at B, and that gives you the solution. So that gives you x equal A inverse B, and this is it. That's how you multiply a matrix and a vector in Python. You can use the at symbol. Okay, try it out. Note that the solution over here is equal to the same as the solution over there, clearly as expected. Okay, it's always good to have 2 or 3 ways of verifying your answer or your method. Okay.
Professor, what did the at do here? Can you say that one more time?
So the at allows you to do how do you do a matrix vector product? So clearly, when you multiply a matrix by a vector, depending on the size, in this case, the result should be a vector, right? Because think of it this way, A inverse times B, the result is equal to X, and X is a vector of 3 components. So the 3 by 3 matrix times the 3 by 1 vector needs to result in a 3 by 1 vector.
1 vector.
3 by 1, yeah, a vector of 3 components. Now, if I do simply A inverse times B, it gave me a 3 by 3 matrix. So I don't know what Python did over there. But clearly, this is not a matrix vector multiplication that I intended, okay? What you really need to do is what's called the inner product, A inverse at B. So that does it correctly. It takes, you know, row, column, row, column, row, column, and computes it correctly, okay?
Okay, thank you.
Okay, and that's it. We could say, you know, that's it. Now we know how to do linear systems of equations, okay? Unfortunately, that only works for very small systems of equations, okay? When you go to very large system of equations, and I'm talking million, you know, a matrix that's 1 million by 1 million in size, or 10 million by 10 million in size, this method is extremely expensive, if possible at all, because the calculation of A inverse is one of the most expensive things a computer could do. Okay, and that's why there is more to say in this chapter. We're going to learn methods to avoid, to avoid computing A inverse, because A inverse is very expensive. Okay, now I can show you here. I left this plot for the end of the chapter, but what I'm going to show you here is a bunch of curves. Don't worry what this is doing. This is just solving a very, very, very large system of equations, okay? On the y-axis, I'm showing you the time, or think of it as the factor, how much time it takes to solve a large system of equations as we increase the number of equations. On the x-axis, we increase the size of the matrix. So 100 is a matrix that's 100 by 100. 500 over here is a matrix that's 500 by 500 in size, okay? Now look at the blue line. This is the cost of using A inverse. See how it exponentially shoots up. The other curves are methods that we're gonna learn, we're gonna get introduced to in class. They're called iterative solvers, okay? Look at this red one over here. That's called a algebraic multi-grid solver. It's pretty much same cost, independent of size of matrix. So if you use A inverse for large system of equations, and even, you know, early on, even like at 50, you know, you're gonna climb exponentially in time, and that becomes very costly, okay? So using A inverse, yeah, it's a way for small systems of equations, but you know what? That's not what you wanna do in engineering applications. Okay. So now we'll go back, we'll continue our journey. We're gonna continue defining the notation. Now that we looked at 3 equations and 3 unknowns, in general, the systems we are gonna be dealing with are huge. They're unlimited in size, you know, potentially they're finite, but they're very large. So typically we're gonna describe the unknowns as x1, x2, x3, x4, all the way to xn. And we're gonna describe the coefficients as A11, A12, A21, essentially Aij. Okay, that's kind of the definition of the matrix. So this system of equations now, you know, can be written as a matrix vector multiplication. Now notice here I have n unknowns and potentially an m by n matrix. I have more equations or less equations than unknowns. Okay, I left this to be as general as possible. Okay. And you can write this simply as AX equal B. Now, entries in the matrix, we refer to them as Aij. I refers to the row, J refers to the column. So when I tell you A35, that's the entry in row 3, column 5 of the matrix. If you forget that, if you forget what I stands for, what J stands for, I always forgot that when I was a student. So I came up with my own notation. I call it ARC. R for row, C for column, or arc. Okay, when you think of matrix, coefficients in the matrix are an arc. ARC is the coefficient in row R, column C. So when I tell you A57, that's row 5, column 7. Okay, keep that in mind. Now, here's the question, going back to Hayden's comment. For this system of equations to be properly posed, in other words, solvable, what is the relation between the number of unknowns and the size of the matrix? So the way I displayed this matrix here, I have n unknowns, but I potentially have M equations. Okay, so what is the relation between M and N? If I have M equations and N unknowns, what should we satisfy for this system to be well posed?
Should be equal to each other.
Yes. Why?
It doesn't have something to do with like degrees of freedom and being overspecified and underspecified.
Sure. Yes. Yes. So this simply goes back to saying we need to have as many equations as there are unknowns. If you have one more equation for the unknowns, you might have more solutions than one solution. If you have less equations, you might not have any solution at all. You have an either underdetermined or overdetermined system. For it to be well posed, to not worry about any of these issues, you need to make sure that for each, in other words, like for each unknown, there's one equation. Okay, that's kind of how you might want to frame it. So indeed, as Abby said, the matrix needs to be square. So the size of the matrix needs to be, the number of rows needs to be equal to the number of columns, and that needs to be equal to the number of unknowns, right? So, you know, when you get a system where you have, where this is off, you got to do some catching, some error catching or diagnostics there. Okay, so now we know, let me summarize what we learned today. One way to assess your learning without going on tangents, one way to assess your learning, and I learned that from Jordan Peterson, is so like right now, compare your knowledge right now to what your knowledge was at the beginning of the lecture. Okay, you might not have learned anything. Or you might have learned because you know the material, obviously, or you did learn a few extra things that you didn't know at the beginning of the lecture. So that's one good way to assess your learning. Now I'm going to help you summarize what we learned so far. We went from 3 equations and 3 unknowns. We learned that all systems of equations can be converted to matrix vector notation, which simplifies how we work with this. Then we defined the solution in terms of the inverse of the matrix. We saw how we solved that in Python. Then we extended this nomenclature to arbitrary systems of equations, and we deduced that for them to be well posed, the matrix needs to be square. There should be as many equations as there are unknowns. Okay. So now when you look at a matrix, what do you say when you see a matrix like this? You say, this matrix probably corresponds to a system of equations. The first equation is given by the coefficients in the first row. The second equation is given by the coefficients in the second row, and so on and so forth. Matrices are just a simplified representation of systems of equations, of linear equations. All right. Now, as we move on, we're going to deal with a bunch of matrices. So it might be worth just defining those matrices. And throughout your career, you're going to see a lot of these matrices as you learn and do things. And I'm going to show some of those over here. The first one on the upper left is just a general standard matrix. Okay, it's filled with coefficients. All right, and we call this a dense matrix. Dense because all the coefficients are non-zero. Okay, now next to it is what we call an upper triangular matrix, where below the main diagonal you have zeros, and above the main diagonal you have non-zero entries. Okay, so that's called an upper triangular matrix. Lower triangular is the opposite, where you have non-zero entries at the bottom, below the diagonal, and zeros above the diagonal. So the missing space in these matrices are zeros. A purely diagonal matrix is one that only has non-zeros on the main diagonal. Okay, the identity matrix, as you probably know, is one where the main diagonal, where everything is zero except the main diagonal, it's all ones. And a banded matrix is one where you have some non-zero diagonals, okay, some non-zero diagonals, but most of the matrix is zeros. Okay, like in this example here, in that I'm showing on this slide, you have the main diagonal non-zero, the first upper diagonal and the first lower diagonal are non-zero. We're going to call this a tri-diagonal matrix. Anyway, okay, so now we know that using the A inverse approach is expensive, and I hope I convinced you of that with that plot that I showed you. But the goal, again, in general, in this chapter, is to develop solution methods for systems of equations, large and small. For small systems, just use A inverse or the solve function and move on with your life. For large system, this is going to be the guts of this chapter. Okay. So in general, we categorize solution methods for AX equal B, or for systems of equations, large and small, as either direct or iterative. With direct methods, we essentially go and try to target A inverse. We go and try to find A inverse directly, okay? And then invert the system that will give you an almost exact solution. And we know it is expensive, but there are a few cases where for very, very, very large systems, you still can do this direct method, but those systems have to be very specific, okay? And that's what we're gonna discuss next. The remaining set of solution methods are called iterative methods. They are much, much, much cheaper than direct methods. However, they only work for certain types of matrices. And we're gonna revisit all of this and where these apply and where they do not. But they only work for specific types of matrices called sparse matrices. A sparse matrix is going to be is not a dense matrix, and we'll define that more rationally next week. But luckily, a large majority of engineering problems result in sparse matrices, and that's why we use iterative methods for those. Okay. So in the remainder of this chapter, we're going to learn both about direct methods for large systems and iterative methods, okay? Now, I still have about 15 minutes. I'm going to give you a 2-minute break, okay? Let's just clock in 2 minutes, and then we will start with a direct method, okay? One of the big direct methods. Okay. Yes, Dallas.
So like for when I'm getting my solutions, for like what we did, I'm getting like some negative values. Does that mean like my matrices is wrong, or like I'm just a little confused?
So that's good critical thinking. Should you get negative values for flow rates? Absolutely not.
No.
The flow rate, it's either 0 or something more than 0. So you probably have something wrong with your notebook. Do you want to share your screen with us, if you don't mind? Let me stop my share, and I'm going to allow you to share your screen. Okay.
Is it your A inverse that has a negative value, or the actual?
The solution.
I'm getting the same with both. Let me see this.
Yeah, your solution is wrong. Okay, so.
Oh, I think it's probably right there. I think I found it.
Okay.
That makes sense.
There you and you still have MySwap. So why don't use NP arrays? Don't use NP arrays. NP arrays, they're gonna mess up the order of the matrix. Don't use NP arrays. Just keep them as lists. Just provide A as it is. So WB1, WB2, WB3. Let me see, and then B. So remove the parentheses, remove A, delete that line for A, remove the parentheses from B. Okay. And your WA, B, C are correct. WA2, WA3. Okay, and total mass. Okay, A inverse. Okay, so it's time. Now let me, okay, A inverse. So print solve. Did you just run it?
Yeah.
Okay, so remove A inverse equal Y. I want to see what A inverse looks like.
Oh, okay.
Yeah, remove this. Okay. Okay, so print A inverse, please.
On your B, you have 1 instead of 10. I don't know if that would affect things.
Oh, yes, it should be 10. That's right.
Oh, and then
There you go.
Yeah, and then
You got it. Okay. Hey, thank you for catching that. Good catch. Okay, you can unshare your screen. All right, see, teamwork. All right, so let's do, let's continue sharing our screen, my screen. Okay. Okay, so the one and only direct method we're gonna learn about, and that works for large systems. So we said that A inverse and solve that we just did in Python, those are direct methods. And I claimed that those methods are not efficient and effective for large systems of equations. However, there are a couple of direct methods that work for very, very large systems, arbitrary in size, but those systems have to be very, very specific in form. And we're going to learn about one of them, and that one is called the tridiagonal matrix algorithm, okay? And it is a very special method, very special recipe for tridiagonal matrices. And tridiagonal matrices, they do show up in many problems in 1D, heat transfer, mass transfer problems. You're going to see them a lot. So this is a great technique to do that, because the advantage of the direct method is that it will give you an exact answer. There is no iteration error. It's going to give you an exact answer. The only error that might show up is a round-off error from multiplication and division, but it is going to give you an exact answer. Okay, it's not approximate. Okay, so we're going to learn about the TDMA method, and we call TDMA as tridiagonal matrix algorithm. It is also sometimes called the Thomas algorithm. So we will use those interchangeably. But as the name designates, this algorithm only works for tridiagonal matrices. What's a tridiagonal matrix? Is a matrix that has a non-zero main diagonal, a non-zero first upper, and a non-zero first lower diagonal. Now, one question that someone asked, what if I have a bunch of zeros in one of the diagonals? Is that okay? Of course, of course. The point of tridiagonal is that you have three primarily non-zero diagonals. Now, once you do problems with heat transfer and mass transfer, etc., you'll recognize that most of the coefficients in those diagonals are actually the same. All of them are the same. Okay, we'll get to see that. Now, the advantage of this matrix is that you don't need to store n squared entries of the matrix A. So you don't need to store all the entries of the matrix A. It's mostly zeros. You only need the three diagonals that are non-zero for a total of 3 times n minus 2, because the main diagonal has n entries in it, the upper diagonal has n minus 1, and the lower diagonal has n minus 2, if the matrix is an n by n matrix, okay? So that gives you a total of 3n minus 2 non-zero entries. Now, what I'm going to show you next is just simply the recipe for the Thomas algorithm. Our goal in this class is not to derive it and understand how we derive this solution method. It was developed a long time ago, so I'm just going to give you the recipe of how to apply it, and I'll share an example in the slides that you have to work out at home, how to apply it by hand. But the critical part is going to be when we do it in Python, because then we're going to take it and apply it to very large systems. Okay, the Thomas algorithm, the TDMA algorithm, tells you the following. Okay, if you have a tridiagonal matrix, we just learned that we don't need to represent the entire matrix because it's mostly zeros. All we need is the main diagonal, the upper diagonal, the lower diagonal, and the right-hand side. Okay, so the main diagonal, we're going to call that D, and it's simply a vector from D1 to Dn. The upper diagonal is designated here by U, and it has n minus 1 entries, because it's one diagonal up, so it loses one element. And the first lower diagonal, which we designate here by script L, okay, that's also a vector. If you think about the diagonal itself, it is a vector of entries. Okay, now what we're claiming is that the Thomas algorithm only needs these 3 diagonals and the right-hand side, and from those it's gonna spit out a solution. Okay, a solution in the order the diagonals are given, right? So x1, x2, x3, and so on. And honestly, there's nothing to describe here about the algorithm except the formulas. It goes in 2 steps. You start from I equal 2 to n, not I equal 1. And you'll see why. You start from I equal 2 to n, and then you start manipulating the entries in the diagonal. So now think of the diagonal entries, each one of them, you write them down as a vector, and then you start manipulating the values. In the first step, you start from I equal 2 to n, and you do the following. You take each entry in di, starting from entry 2, and you say this is equal to di, which is the existing entry, minus ui minus 1, li minus 1, di minus 1. So you take elements from the upper, lower, and the main diagonal. Okay, and you combine them and you update the value of di. Then you go to the right-hand side bi. You take the existing value of bi and you subtract from it this one, bi minus 1, li minus 1 over di minus 1. You do all of these all the way to n. It will become easier, more concrete when we do the example, okay? So once you reach dn, okay, and bn, you're done with step 1. The algorithm, that's what the algorithm is. We're not going to derive it, but it's a simple recipe. Okay, where does this recipe come from? We could spend hours deriving it, but that's not the point here. Is that this recipe exists, we trust it, let's just take it and use it. Once you're done with all the D's and all the BI's, now you modified your original diagonal and your original right-hand side. Now you start building out the solution. The way you build out the solution, you start from the end. We're going to start with xn is going to be the new bn, which is we just calculated, over dn, the new value in dn. And then you go backwards. You go n minus 1, n minus 2, all the way to 1. Okay? And you construct your answers. You do xn minus 1, xn minus 2, and it's simply this formula. Okay, over here. Okay? It's kind of interesting presenting it this way. It's a recipe. The only way it's going to stick in your head is if you actually do an example. Okay, so I'm going to give you this example. Yes.
Question.
Yeah.
Where does the B come from again? Where? Because I see
B is the right-hand side. B is this guy.
Oh, the
right-hand side of the system, right? Yeah, it's the right-hand side of. So we're going to agree on this nomenclature. A is coefficient matrix. X is unknown vector. B is the right-hand side. Okay, now A is made up of D, which is the main diagonal, U, the upper diagonal, L, the lower diagonal. So if you take this equation, okay, this system of equations, the first step is to make sure that it is a tridiagonal system. And indeed it is, okay? So if you write this in matrix form, you'll recognize that this system that we're gonna do as an example is actually a tridiagonal system. Now, we're not going to do this in class. Typically, when I have a board, you know, in the classroom, we can kind of work through it on the board. But on the slides, I want you to try to do it by hand. I'll just go through a couple of steps with you first, and then please make sure you do it by hand, because this is a type of question I might ask on the exam, okay, for a small system of equations, doing it by hand. So first, you want to make sure that it is a tridiagonal system. And you ask yourself, is this tridiagonal? What do you think? I say it is tridiagonal because the main diagonal is non-zero. The first upper diagonal, first lower diagonal, everywhere else is zeros. Could you have a 0 on one of those diagonals? Of course you could, okay? But you might get in trouble actually with division by 0. So you shouldn't have a 0. Okay, so if you look at it here, you cannot have a 0 on the main diagonal, okay? You could have a 0 on one of the other diagonals, but not on the main diagonal. Why? Because you would be dividing by 0 over here, okay? You might be dividing by 0. Okay, so first you convert it into tridiagonal. Now, with the Thomas or the TDMA algorithm, you need to define the lower diagonal, which is 1, 4, 2, the main diagonal, 2, 2, minus 1, minus 1, and the first upper diagonal, minus 3, minus 1, 0. Those are just the vector. Each diagonal is a vector, can be written as a vector. Once you write those, then you know L1 is what? 1. L2 is 4. L3 is 2. D1 is 2. D2 is 2. D3 is -1. D4 is -1, correct? Yeah, same thing for you. And then the vector B is -4 to 9, 2. So the indices that you saw in the recipe for the Thomas algorithm, they just correspond to the indices of the matrices of these vectors, starting the count from 1. We're not starting from 0, okay? We're not starting from 0. Okay. Next, we implement the TDMA. Step 1 says we start from I equal 2 all the way to n. In this case, what is n? It's 4. Okay. So for I equal 2, we have this formula. So the formula is for di, but what we do, we just say d2 is equal to the old value of d2 minus u1 L1 over d1. The old value of d2 is 2, and then u1 is -3, L1 is 1 over 2. It's just simply accounting for numbers, okay? And then you get the new value of d2 is 7 over 2. And same thing for b2. You do is equal b2 minus b1 all 1 over d1, and you get this number. You repeat for I equals 3 and for I equal 4. It's just a matter of keeping mental accounting. There's a lot of algebra. Make sure you don't make a mistake. But I urge you to do this example at home by hand. Okay? Take the formula, apply it. Okay? If you want to play around with the matrix, change the coefficients in the matrix, and then try to get the solution, but then verify it in Python using the A inverse. Okay? Now, step 2 is when you compute this actual solution. You start with n, and then you go backwards. So at n equal 4, in this case, we start at I equal 4. X4 is B4 over D4. It's 4. And then I3 to I equal 1. And the answer is simply 1, 2, 3, 4. That's your answer, okay, for this system of equations.
Professor, could you show us that code in the Python? I know that you gave us the LSOL
yes.
activity too.
Yes, I'm going to share that code in Python. We're not going to be able to do it today because we're running out of time, but we're going to do it together next Thursday. Okay. Again, the goal here is for you to just exercise your thought process in the iterative, it's not iterative actually, in the recipe of doing the Thomas algorithm. Okay. So what I have 2 questions now for you. Question number 1 is, how would you verify that this is a solution for the system of equations? Let's say you change the coefficients in the matrix and the right hand side, and you want to play around, see if you can get the right solution. How can you check that you got the right solution?
Plug your values back into the original equations.
That's good. Yes. So Sami is saying you put the values back in the original equations. What if that was a lot of algebra? Okay. So even 4 equations and 4 unknowns is quite a bit of algebra. So what would be another way to verify?
You could use a different method in like coding, I guess.
Yeah, so which one in coding? So Abby is saying, okay, we're going to put this in the code, but use another method. Which method did we learn so far?
Well, we looked at 2 where we used the solve
yes.
Python.
And A inverse, yes, that's it. So when in doubt, always go back to that A inverse or solve, and make sure what the work you did by hand corresponds to the work, to what a code that's been verified and double checked is going to give you. So I would take these equations, this coefficient matrix, put it in Python like we did in the first example for separations. Okay, just put those coefficients there, run the solution, and see if you get the same answer you got by hand. That's a great way to double check your work. Okay, now I have another question before I let you go. What types of errors are present? So remember, we talked about iteration, round-off, and truncation errors. So let's start with iteration error. Let me actually maybe make a poll. Oops. Apparently, I cannot do polling. I cannot do a poll. Okay. Any volunteers for the types of errors that we have over here? Do you have truncation error?
I don't think so.
Why not?
Because if I remember right, truncation errors when. Here, 1 second. Let me check and make sure I'm thinking.
I'll help you. When you take an exact mathematical expression and chop it, Dasha is volunteering. Do you want to add something?
So I do think that we have truncation error because truncation error is because of a mathematical formula, and isn't the Thomas method a mathematical formula that we get truncation error every single time we
So we
calculate?
got now two contradictory statements. This is interesting.
Not chopping it off, right?
We're not chopping it off. Hayden is so Dasha is saying there is truncation error because when we define truncation error, we defined it as taking an exact mathematical expression and truncating it. But Hayden is saying we're not truncating anything over here. We're not even taking an exact mathematical expression and truncating it. So who's right? Okay, I'm gonna have to side with Hayden. Okay. Oh, Dali had to say something. Go ahead, Dali.
Oh, yeah, I was going to say, I think Hayden's right, because I don't think, so I think a truncation error would be if we were doing like a continuous sum, like out to infinity. And unless our matrix was infinite, but it's not.
Or something like that. So yes. So there is no truncation error because we did not take, we never in any of the steps we did today, did we take an exact expression and truncated it. Now, this is based on the fact that the Thomas algorithm, when those formulas are exact, and that's what it is claimed, and they are exact mathematical expressions. Never did we truncate them anywhere, okay? So there is no truncation error, absolutely none in the Thomas algorithm, okay? What about iteration error? So remember iteration error, take the book, you start somewhere, and then you're like, I'm finding the letter M, then, I didn't hit M, so let me repeat that formula and then repeat it again and then repeat it again. Do we have iteration error here? I cannot see all of you if you're raising your hand, but just feel free to speak up.
Well, I feel like it's an iterative process because like in step one, we're taking what we got as a result. So on like I equals 3, we're taking what we got as our result for I equals 2 into D3. So I would say it's an iterative error. There's a potential for it at least.
Okay, so Porter is saying there is iteration error involved. So let me ask you, Porter, it looks like we're doing iteration, but are we? So think about this. When we computed D2 or DI from this formula here, we computed it once. Did we refine it?
No.
No, when we computed D3, when we computed D4, when we got the solution, we got X4, we computed it once. X3, once. Did we refine it? So if you take the analogy of trying to find the letter, we hit it spot on.
Oh, okay.
So now, do you think we have iteration error?
No, I'm going to backtrack.
Yeah, we do not have iteration error. Absolutely none. Okay. What about round-off errors?
Wouldn't that depend on the results we're getting for either of the variables? Like if we got like 1/3 and it was like 0.3 repeating, it would chop off.
Okay, very interesting, Rob. So for this particular example, there is no round-off.
This one, it doesn't look like it, no.
Dealing with integers, correct. But in general, yes, there is round-off. Anytime you multiply floating point numbers, divide them, subtract them, there is round-off. That's it. It's by anything that involves a numerical operation has round off. This example only, specifically, we did it by hand. We kept all the fractions complete. There was no round off. But in general, you apply the Thomas algorithm and you have a bunch of floating point numbers, you are going to have a lot of round off. Well, you're going to have round off. Okay. All right. So I'll let you go here. Thank you for bearing on for a few more minutes. I'll stick around for a few minutes. If you have questions, feel free to step out, and office hours again today at 3:30. Thank you for your kind attention. Bye-bye.